right there. Also, I realized that my the setting for the homework was off. So it shows that it's due tomorrow when it obviously should have been due yesterday. But half of you already signed it, put it in, so that's all great. Obviously, I'm not gonna ding anybody for handing it in afterwards because that's what I said. That's what I said. But please remember that it's always due, or it's always supposed to be due before the beginning of next class. So if it's not due before the beginning of next class, then just shoot me a quick email saying, "Hey, I think you have your setup wrong," all right, so that I can fix it. Is there a rule today to wear a hat? Just see everybody going through. So if they run out there and get my hat real quick, I'll pass on that one. All right. I guess only the people who put their cameras on have hats. People who, even if you don't have a hat on, you can put your camera on. That's totally acceptable. All right. Then, are there questions from last time? Right. Last time we started talking about tolerances, and we went through what tolerances look like in inches. And you were supposed to, fill out these tables. And if you didn't do it yet, we can do it after you finish it. We should have enough time to finish both the assignments for today and whatever's left over from last time. But let's get that started. So we talked about the all of that. 1 second, myself confused. Where's my Zoom? Share my screen. There we go. So last time we talked about everything in inches, right? And so a reminder again that as long as we're working in inches, our formatting is very specific, right? The formatting is that the main one is that we have no leading zeros, right? So 0.5 is 0.5 in that system. But now we'll look at a whole shaft system in millimeters, so based on a different standard. The good thing is that, of course, limits, basic size tolerances, and then those last two are all the same. Does anybody remember what MMC and LMC are? Those stand for? Well, back to our short-term memory. Or I guess it's Thursday, so it's longer ago. And it was before the holiday, of course, everything's gone now. The MMC was the maximum material condition, and LMC was the least material condition, right? So which of my two diameters gives me the most or the least material, right? And we're talking about a hole in the shaft. So for the hole, which of the two, the maximum diameter or the minimum diameter, gives me the maximum amount of material for the hole? Which one?
The maximum.
The maximum gives me the most amount of material.
Uh-huh.
Yeah, let me see if I can get my pen to work on here. That looks like it should be. Where did it go? There we go. There we go. Pen pad a little small for the screen. So if I have some kind of a part, like we had a nice little rectangle, and I have a hole in it. We said that based on tolerances, right? I'm not sure exactly how big that hole is, so that hole could be like the smaller diameter or the bigger diameter, right? Kind of my tolerance. So which of these, the smaller or the bigger diameter, gives me overall more material in my part? Right, if I have the smaller hole or if I have the bigger hole. I'm thinking about this entire part. In which condition will it have more material?
The smaller hole.
The small hole, right? So for the hole, the MMC is the small diameter. And of course, for the shaft, it's the big diameter, right? If I have a shaft, then the bigger the diameter is, the more material I'm going to use, right? So remember those that kind of little difference there. But the good thing is that all these are exactly the same in millimeters as they were for inches, right? So we don't have to learn anything new. Just have to remember that for our formatting, we now write leading zeros. The good thing is in millimeters, we don't run into leading zeros all that much anyway, because anything millimeters is very, very, very small, right? So a single millimeter is already small, so we usually don't have to worry about this. All right, let's do an example. That looks very much the same as before. So we have a shaft that has the limits of a diameter of 4.9, 4.8, and a hole that has the diameter of the limits of its diameter of 5.2 and 5.0. So we can fill out our same table again as we did before. What would be the limits for the shaft?
4.8 and 4.9.
All right, those are the correct numbers, but remember what we do when we write down the shaft limits.
4.9 minus 4.8.
All right, so we write the larger one first because that helped us later on to do those subtractions in an easier way. All right, so 4.9, 4.8. How about for the hole?
That one is the other way around.
Exactly, right? So it'd be 5.0 and 5.2. Then what is the basic size for this one?
It's the subtraction of the biggest one minus the.
That'd be the
I
tolerance.
don't mentira, never mind. Never mind. No.
The
That's the
basic
tolerance.
size was kind of right. We have to.
The basic size is like the average, like of the size, like but I remember how we chose that one.
So like the basic size is, imagine you're trying to build something, right? And so you need to get these bolts or screws or whatever it's going to fit into your system. So you go to the hardware store and you're going through the aisle and looking for these bolts, right? And so you're not going to find a bolt that has a diameter of 4.9, right? So we're looking for something that's kind of exactly, in this case 5, right? Something that's a nice round number that we'll be able to buy somewhere else, right? So the basic size is kind of the nominal size, right? Kind of the easy one to find. In this case, as you're saying, would be 5. And now the tolerance, how do we get the tolerance?
That's one with the subtraction. Biggest one minus the
For
smallest
each
one.
of them, right? So the large diameter minus the small diameter for both the shaft and the hole, right? Very good. Remember that the tolerance is always going to be positive, right? So we always do the bigger one minus the smaller one. All right, so that was what we did before. Now we can do our maximum material condition and our least material condition. What's our MMC for the shaft?
.9.
Exactly, right? The bigger. So that means the least one is going to be 4.8. How about for the hole? The maximum one
5.
is 5, right? The lower of the two, and then 5.2. Now, who remembers how to figure out the maximum and the minimum clearance?
I think it was the LMC of the shaft minus the one from the hole.
For the maximum? Exactly. And for the minimum is the same with the MMC.
Yeah.
Right? You can remember it with LMC or MMC. I like to remember it again that I just say, well, the maximum clearance is just the largest possible hole minus the smallest possible shaft, right? Which is of course the LMC, right? So it would be, in our case, it would be 5.2 minus 4.8, so that gives us 0.4. Now for the maximum minimum clearances and for tolerances, we will have a 0, right? But see here that this 0 now is there, right? We do put the leading 0 there, and then the opposite for the min clearance. Now, based on these two, what do we have for what kind of fit do we have? Both clearances are positive.
Wasn't it clearance? or something like that.
Yeah, the fit is just clearance. What were the other two?
Transition and something else.
Transition, exactly, and the last one, there's two more, but the other one that we mainly use, or the line one we said we don't use very often. Right, so on the one hand, we have clearance where both are positive, right? So there's going to be potentially a little wiggle room between them. Then you said transition, that's the one where
Interference.
sometimes interference, very good. Right, so that's the one where basically, even if it's the largest hole and the smallest shaft, it's not gonna fit. Now in our case, we have both the max and the min clearance are positive, so we know that has to be clearance. All right, now for the metric ones, we have another set of variables that we calculate, and that's the deviation. So basically, how far off am I from my basic size, right? So we do the upper deviation, we just do the basic size minus the upper, like the larger diameter, and for the lower deviation, we do the same thing, but with the small diameter. And we take the absolute values, right? The deviations are always going to be positive. And then the important thing is what we want to find at the end is what we call the fundamental deviation, and that is the smaller of the two. And we're actually going to see later that that's kind of what we use to then write the definitions of these fits. All right, if we go back here, if we do our upper and our lower deviations and our fundamental deviations, then what do we get, right? For our shaft, we said we were going to do for the upper one, it would be the larger of the diameters minus the basic size, right? So the upper for my shaft up here, right? The upper one with 4.9. So it'd be 4.9 out of 5 minus 4.9 is 0.1, right? Or I can do 4.9 minus 5, gives me minus 0.1, but it's absolute, so it's 0.1, right? So this is how I get my upper deviation. Now through the lower deviation, I do the same thing. So it'd be 5 minus now the lower diameter, right? Gives me 0.2. That means my fundamental deviation is just, again, the smaller of the two, right? In our case, the smaller is 0.1. So my fundamental deviation is going to be 0.1. And then the same for the hole, right? For the hole, I take my basic minus my upper. So that'd be 5.2 minus 5, 0.2. And then 5 minus 5, because the lower is just 5, gives me 0. So what's my fundamental deviation for my hole? A 0. Yes, good to have the camera on. See, if you're doing something on the camera, I don't see it. I don't see all of your faces all at the same time. So if I'm not reacting to something that you're doing, just speak up. All right, so this is how we get our fundamental deviation. And again, this is something that we'll see in a minute, is going to basically tell us how we're going to kind of describe what our fit was, right? Remember for the inches one, right? We had FT2 and FN and all that kind of stuff. And for the metric ones, we'll have something that looks a little more elaborate, but it goes the same way. And this is just kind of the overall view of what we had, right? This is a summary of all we did: the limits, the basic size, tolerance, upper, lower deviation, fundamental deviation, and then the clearances and the fit, right? So that's just all the stuff that we did. All right, now the fun starts, right? This was easy math, but ISO likes to have some really, really crazy ways of describing their fits. So what we're going to need is the International Tolerance Grade number, the IT number, and that indicates the tolerance. The smaller that number is, the tighter the tolerance, right? The tighter the tolerance means less kind of extra space. And then the tolerance zone is a letter code that we kind of use to say where that tolerance is, right? Is it going up? Is it going down? And then that tolerance zone has an uppercase letter for the hole and a lowercase letter for a shaft. And it's always a whole shaft. So we'll see that. And so what is it based on? Well, it is based either on the hole as a basis system or on the shaft as a basis system, right? If I have the hole as my basis system, then if my shaft is smaller, it's clearance. If it kind of overlaps, it's transition. And if it's larger, it's interference. And the same the other way around, right? But in one case, I'm using the hole to base everything on. And in the other case, I use the shaft to base everything on. Right, so whichever I have a better handle on, that's what I'll be using. All right, let's kind of practice this just for a little bit. And let's see how easy we can or fast we can be about getting our type of fit. Right, so if I give you this shaft and this hole, what type of fit do we get?
Clearance.
You get a clearance.
Okay, I heard 15,000 clearances there. Why clearance?
Because it's positive.
What is positive?
The shaft and the hole.
Both are positive. The other way that we could see this is we could say that as long as the smaller one with the minimum clearance, if that is positive, then we know it has to be clearance, right? So in our case, the smallest hole and the largest shaft still give us a positive number, so we're good, right? So that's definitely clearance. Now, what would you say is the basic size for this one?
Five.
Exactly, 5, right? We have 5 as a nice round number here. You will see in all of these, once we go into the metric ones, that one of my four limits is always going to be the basic one, right? So in our case, the basic's 5. And because 5 is one of the measurements of the hole, we call this a hole-based system, right? So it's a hole system. Now, how about the next one? What do we get here for a fit?
Clearance as well,
No, transition.
or transition.
For the two.
Transition.
Transition, you get
Okay, I
negative.
need to transition the background. Why transition?
Because you get a negative.
I get a negative for the minimum, right? Because it'd be 60 minus it. All right, so we get transition. What's our basic size?
60.
60. And then is it a hole system or a shaft system? Right, so again, I can't skip back to the previous slide because this is all separate bits here. But remember, right, so we said that whatever has the fundamental deviation of 0 is the one that gives us the basic one, the basic size, right? So whichever one where the limit is the same as my basic size, if one of the limits is the same as my basic size, I know that what defines the system, right? In the first example, we said, well, on the hole, right, we had the basic size of 5, and one of the limits of the hole was 5. Now we have a basic size of 60, and we have which of these has, one of the limits is the same as the basic size. Well, obviously, we have the 60 here, right? So that means it is also a hole system. All right, next, what do we get next? Or maybe we'll try to explain that again because Gloriana is looking very, very unhappy with what she sees. Is there a specific question or somebody walked by who gave you a nasty look?
No, I'm confused with
Okay.
how to determine like the system of a shaft or a hole.
All right, let's see if we can scroll back here for 1 second, right? So this is the previous slide, right? So if I look at kind of this here is supposed to be the shaft, right? And I can see now that one of the limits of my shaft, right? My shaft could be somewhere here, this diameter, or it could be up there, that diameter, right? Somewhere between there. Those are my two limits. Now, but one of the limits that I have is it's the same as the basic size, right? So if I have that, then I say, well, that means my system is a whole basis system, right? So it's based on the whole. The same thing here, right? If I have the shaft, and you can see my shaft could be somewhere, is anywhere between these two, right? The diameter of this is anywhere between these two. But if one of them is the basic size, right? If one of the limits is the basic size, then I say it is a shaft-based system. Right, so if we go back to, we were somewhere here by now, right? If we think about here, we said, well, in this case, the whole, one of the limits of the whole was the basic size, right? So that's why it's a whole-based system. Here, again, the whole had the basic size as one of its limits, so it's a whole system. Does that make more sense now? That's really pretty straightforward. Right, it's just like once you have it, you have it, right? All right, so now how about the next one? What type of fit do we have for our next
Transition as well, I think it's negative.
Well, what if which one is negative? The max or the min clearance?
Both of them.
Both of them are negative. What does that mean for my fit?
Interference.
Interference, exactly. Right, so it should be an interference fit, right? Again, we would be doing 19.953 minus 19.998, right? That's negative. We don't have to know exactly what the number is for in this case, right? We just need to know it's negative. And we can say that 1987.5 minus 20, of course, also is a negative number, right? So it's really fast to do. And so we can say it's interference. Now, what's the basic size for this one?
20.
20.
Right, exactly. And what does that mean for our system? Is it a whole or a shaft system?
Whole
Yeah.
system. Yes.
I heard whole, I heard shaft. Who wants to say, who wants to give it a strong?
Which one was the one that was the same?
It's based on whatever, like, you know, one of the limits is going to be the basic size.
But which one, like the one that was the same?
Yeah.
Is the one we have here.
Right?
I'm confused.
So we have, in total, we'll have 4 limits, right? We have 2 limits for the shaft and 2 limits for the hole. One of those 4 is going to be equal to the basic size. And for these fits, for these defined fits, that's always going to be the case. And whatever limit on there, right? Upper, lower, doesn't matter. But if it's the limit of the shaft, that is the same as the basic system. It's a shaft system. If
Okay,
it's
so it's a shaft system.
okay, so we all agree now that this.
Professor, what happens if there is a limit that is the same in shaft and hole and it's the basic size? Like, how do you?
Don't, that's within the, so these again, right? These are going to be all numbers that are defined in one of those isonorm tables, right? And so there is no isonorm that has the shaft and the hole both have a 0. I don't think so. I should probably go back and double check. But I guess in that case, if you could, I'll check on that one. I don't think that we don't have double H's, I think, in our tables. But in that case, it'd be tricky. I'll make sure that neither of the certainly the homework assignments and exams will not have that little extra bonus case. All right, so now we've kind of figured out what a hole and a shaft system are and what basic systems are. So now let's look at our notation, right? Remember that for the ones that we had before, right? The inches one, we had like FN2 and all those kind of different things that look pretty simple and straightforward. Now the metric one is a little more difficult to read. And so for that one, we'll get something that looks like this. Diameter 10 H9-D6. And of course, everything in here means something, right? So the easy one is the first one, right? That's just the basic size, right? So that's going to be the basic size of 10 millimeters in this case. Everything here is millimeters. Now, the next two that we see, we call the hole tolerance zone and the shaft tolerance zone. It's always going to be hole, shaft, hole, shaft. And remember that capital means hole, lowercase means shaft, but it's still always going to be in this nice order. The letter represents the fundamental deviation, right? Remember, we talked about fundamental deviation just a couple minutes ago. It's basically how far am I away from my basic one, right? That has different letters, and you can go look up what each of those letters mean. And then the fit number here is again the international tolerance number that basically says how close, like how small is my tolerance, right? This gives the deviation, this gives the tolerance. This gives these very interesting looking setups. And so if we have a notation like this, then we could go into a table. Again, there's a whole set of tables. I've added these tables or a copy of these tables to the materials section on Blackboard, just because the books, I don't like the table so much because you kind of have to, there's a scroll button at the bottom, so you can't really see them all at once. But they're all going to look like this, right? So you're going to have the basic size here. Now you'll see the difference between the metric and the inches one, right? The inches had ranges, right, from 0.5 to 7.5 inches or something. Here it's given as separate numbers, right? So if you were looking for something a basic size of 1.1, right, then that just doesn't exist, right? So you'd have to either choose 1 or 1.2 in this case. And then you'll see these groupings, right? And though they're given names, but we're not gonna think about those too much, right? You always get the hole and the shaft. You can see that the hole has the capital letter, and then you can go in here and you can look up whatever you need to look up, right? So in our case, we're looking for a diameter of 2, so that'll be this row down here, and then we're looking for an H9D9, H9D9, right? Be careful that you don't get those two mixed up. And so we know that these would be our limits, right? So I would know my hole has a limit of 2.025 and a lower limit of 2, and then the shaft has these other ones. Now, based on this, is this a hole or a shaft-based system?
A hole,
Hole, why hole?
because the basic size is in the limit of the hole.
Exactly here, right? That's what it is. You will also see as you go through this that the system is always what the H, where the H is. Because H basically means that it has a 0, the fundamental deviation is 0. That's what the letter H means. Can be an upper or a lowercase h. Uppercase H means it's a whole system. You see a lowercase h, it's going to be a shaft system. All right, that's how it goes. Now, really, I guess we're going to go through it step by step, right? So let's take the numbers that we have here, stick them into our table, right? Again, for the shaft, we do the bigger one first, right? It's just the numbers that we have in our table. Now, a little tricky is that in most of these ISO tables, you'll see that the hole comes first and then the shaft, whereas most of our tables, it's the other way around. So make sure that you don't put the shaft and the hole numbers in the wrong direction, right? So you have 1.980, 1.955, and then for the hole. All right, so that means we can easily find our tolerance, right? We just subtract those two. Same here. In this case, turns out they're both the same. Now, we already said that it was a whole system, right? Because we have the basic size right here in the hole. And we said that we have a capital H. And then what do we have for a fit?
Clearance,
Why would you say clearance?
because it's positive both of them.
Both are getting positive, right? You can, again, this one is really easy. If you just look at the shaft versus the hole, right? everything in the shaft is smaller than anything in the hole, right? All these numbers are smaller, so we're pretty sure, right? So if these two subtracted are a positive number, then these two subtracted have to be a positive number too. So we're good. So we're definitely in clearance. All right, let's try another one. Let's say P7H9, right? And a diameter of 25. So we go through here, all the way to the bottom, we have our 25. And then we have to go through and see P7 and H6. Well, we have a P7 here, our H6. So we get that. Now, even without looking into our table, right, we can see straight away that this has to be a shaft system, right? Because the H is with the shaft, not with the hole. Remember, if the hole is first, the shaft is second. The hole has a capital letter. The shaft has the lowercase letter, right? So we know it's an H, so it has to be. And we can see also that we have the 25 there in the shaft. So let's stick everything back in here. So that would be the first thing. Again, this is just getting it straight from our table, right? We have our table here. Just put those numbers in. So we have the shaft, which means we can get the tolerance for the shaft. We can get the hole, tolerance for the hole. We already said that has to be a shaft system, right? We can see our deviation right here, our basic size right there. So it's a shaft system. Then we can get our maximum clearance, which of course is the biggest hole and the smallest shaft. So that gives us a negative number. Also get a negative number for the min clearance, which of course means we have, oops, wrong way, an interference fit. Right, very, very straightforward to fill out these tables. Now, from a formatting standpoint, remember that we're now with inches, so we no longer have to get rid of our trailing leading zeros, right? If we have 0 point something, right, we have it right there. But the same as for the metric ones, for the inches ones, we have to make sure that all of our digits after the decimal points are consistent, right? So if I'm in my tables, let's go back to the big table, right? So in these tables, I'm given 3 digits after the decimal point. So in my table, everything has to be 3 decimals after the 3 digits after the decimal point. It all needs to be consistent. Any questions? There was something in chat again. If you're putting stuff in the chat, I'm probably not going to see it until later. So if you just want to shout stuff out, that's the better way to do it. Now, any questions about any of these? All right, then I'll let you try them on your own. So you can see the assignment on Blackboard. So basically it's this table right here, right? The same thing that we did before. In this case, we're given what the 4 limits are, right? So this would not be a fit that is based on any of those ISO tables. But still, we have all the information. You can plug all the information in. And then the second one is going into the tables and finding what these values are and sticking. Any questions there? All right, then I will let you start working on them. Again, the table for these is going to be in the material section on Blackboard. Unless you want to use the book. You can use the book, but for me it's a little uncomfortable. All right. Then I will stop the recording.